So AP Calculus can be divided into four big ideas. The first one being limits. Of course, it's the unifying idea of all of calculus. Then we move on to derivatives, and then from derivatives, we go to integration. Integration, you're going to see, is its major concern is about area underneath of a curve. And then finally, we've got series, and the series, of course, are for the BC only students. Now, again, limits carry through all of those things. And right now, with the integration, what we're going to do is we're going to try to define a very systematic way of finding an area underneath a curve. Okay, and we're going to do that with Riemann sums. Our first objective is to use sigma notation to write and evaluate a sum. If you've never seen the Greek letter sigma, you're just about to. And the second part is that part about finding the area underneath the curve. So we're going to define what the area of a plane region is, and then be able to find it with this thing called a Riemann sum. Okay, Riemann was a German mathematician, of course, who symboled all of this stuff. So with our warm-up exercise here, we want to find the sum of the integers from 1 to 5. So one of the things that you could do, of course, is go 1 plus 2 is 3, and then I go 3 plus 3 is 6, and so on, right? You could just add them up in order. Or we can approach this problem in a slightly different way. So what if instead what we do is we stack our numbers, we go up to 5, and then we count backwards from 6 to 10 and stack them underneath each other. How would that help us? Well, take a look at each one of these columns. Each one of these columns here totals up to 11. That's very convenient, right? So the guy who discovered this was Gauss. If you might remember this back from geometry, it was one of the activities that we did in connection with inductive reasoning. So Gauss was able to discover this when he was a little kid. Okay, so you can see very simply here that in order to add these numbers up, when we arrange them like this, we have 5 columns here. Where's my laser pointer? Come on. There we go. We have 5 columns, and each one of those columns totals up to 11, so obviously we've got 55. Now, in sigma notation, this is the way that I write it. So down here at the bottom, I equals 1. This is your starting place. I is the counter. It's the index. And we're going to count up to 10, and we're counting I. Since I matches up our counter, it's just like here's 1, and now I increase by an integer, go to number 2, and I increase by an integer, go to number 3, and I'm supposed to keep going until I reach the number 10. So it's a fancy way of writing, or a compact way of writing 1 plus 2 plus 3 plus 4 all the way up to 10, right? Again, this was discovered by Gauss as a wee lad when he was, I don't know, in elementary school, middle school, something like that. All right. I don't know if they had school and those kind of, divisions in Germany in those days. I haven't a clue. All right, so let's extend this just a little bit. Find the sum of the integers from 1 to 100. So we're going to use the exact same Gauss technique, stacking the numbers. We're going to stack them up by counting up halfway. We're going to count up to 50, skip a few, and then start counting backwards. And take a look at each one of these columns this time. Once again, they all sum up to exactly the same number, in this case 101, all the way down. Okay, so if I wanted to sum up the numbers from 1 to 100, let's see, how many columns do I have? I can see that I've got exactly, let's count them up, shall we? 1, 2, 3, 4, 5, skip a few, 49, 50. There's 50 columns. Each one of those columns is 101. So you multiply 50 times 101 and you get 50, 50. And so here again in sigma notation is how that thing is written. This is the sum. This is the Greek letter sigma, capital letter. Sum from I equals 1 to 100 of I is equal to 5,050. So this is actually the answer to the problem. This is the legendary problem that Gauss was presented whenever he was in school. His teacher was asking the kids, oh, let's I'm going to give you some busy work here. What's going to take you a really long time to do? Okay, why don't you guys add up all the numbers from 1 to 100, okay? And when you're done, you go ahead and bring me your little blackboard. And of course, he did it in minutes because he did it like this. Super smart guy. Okay, considered by many people as being the smartest mathematician who was ever alive. Let's see if we can generalize this. So instead of going up to 10, instead of going up to 100, we're going to go up to n. So 1 plus 2 plus 3, all the way up to you just pick the number where you're going to stop. So we're going to do it exactly the same way, just in general. So what we did on, let's say the previous one, we stopped at 50. We stopped at 50 because we were going halfway up to 100. So on this one, if we're going up to n, halfway would be n divided by 2. So that's what we're going to do. Sprinkle in some numbers. I start counting on the top row, 1, 2, 3, skip a few, and I'm going to go all the way up halfway to my starting or to my ending place, and then start counting backwards on that second row. How does that help me? We'll take a look at each one of these columns, add each one of them up. So here I have n plus 1, n minus 1 plus 2 would be n plus 1 again. N minus 2 plus 3 also gives me n plus 1. So you can see that I've got n plus 1 for each one of these columns. Well, secrets. All right, and then how many of these columns do I have? Well, just like the previous one, it's whatever this number is, that's how many I have. It's halfway to n, so it's n divided by 2, and then each one of these columns multiplies up to n plus 1. So here's our formula. Usually we write it like this, n times n plus 1 divided by 2. So in sigma notation, this is what it looks like. It's the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. So in other words, we have just developed a formula that will add up all the numbers from 1 to, any kind of ending place in terms of some sort of integers. And we'll use this formula actually whenever we start talking about these things called a Riemann sum for the second objective. Okay, before we get there, this is a warm-up exercise for the first objective, being able to use sigma notation to write and evaluate a sum. And the picture right there, that is the big old Greek letter sigma, which in mathematics we use to represent a sum of a whole bunch of things. There's a related one for products, and it's the capital letter for pi. And just like a summation is you add up all those numbers, and the product one would be the product of all those numbers. Not that we're going to do that. No, we're just going to add up a whole bunch of things because that's super fun.